Long before anyone learns to smelt iron from stone, human beings are already holding iron in their hands. The strange part is that some of it has fallen from the sky. You stand beneath a night sky untouched by electric light, where every star seems sharp enough to cut the darkness. Somewhere beyond the horizon, a blazing object tears through the atmosphere. It flashes brighter than any torch, roars overhead, and vanishes into the earth with a force that people nearby will remember for generations. Later, someone walks across the scorched ground and finds something deeply unusual. It looks like stone, yet it feels heavier. It is cold, dark, and strangely metallic. When struck, it does not crumble like ordinary rock. Under a hammer, it slowly changes shape. You are looking at humanity's first iron. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you settle in, tell me where you're listening from, and what the local time is where you are tonight. Now, dim the lights and let your mind drift backward into a world where iron is not yet dug from mines or poured from furnaces, because no one has the faintest idea how to make it. For most early communities, metal itself is already something remarkable. Stone is everywhere. Bone is familiar. Wood can be cut and shaped. Clay can be fired. But metal behaves almost like a substance with a secret personality. Copper, when discovered and worked, can be hammered. Later, people learn to melt it. Bronze eventually follows. Those metals come from the earth, even if extracting them requires knowledge, patience, and a respectable amount of smoke. Iron is different. The iron that first reaches human hands does not necessarily come from underground mines at all. It comes inside meteorites. You might pick up such a meteorite and notice its extraordinary weight immediately. A lump no larger than a fist feels oddly substantial in your palm. Its surface may be dark, rough, and pitted from its fiery journey through the atmosphere. Or polish it, however, and a silvery interior appears. Some iron meteorites contain large amounts of iron mixed naturally with nickel. That nickel is important because it gives ancient meteoritic iron a chemical signature that archaeologists can identify. Thousands of years later, records confirm that some very early iron objects contain unusually high levels of nickel, strongly suggesting that their metal came from meteorites rather than smelted terrestrial ore. This means iron objects exist long before the beginning of widespread iron smelting. Imagine how mysterious such material must seem. Nobody sees a mining crew carrying it out of a hillside. Nobody watches a furnace master produce it. One morning, perhaps after a terrifying light crosses the heavens, an unfamiliar lump simply exists where there was no lump before. It is not difficult to imagine stories gathering around it. A stone from the gods, a fragment of the heavens, a piece of a fallen star. Of course, ancient people do not need a modern scientific explanation to recognize usefulness. Human beings are exceptionally good at hitting unfamiliar things with other things until something interesting happens. Gentle archaeology, if you like. A craftsperson places this strange celestial stone on a harder surface and strikes it. Instead of cracking cleanly like flint, part of it flattens. Another blow changes it further. That is an astonishing property if your daily tools are made from materials that chip, split, or fracture. You can hammer this substance, you can reshape it. You can perhaps sharpen an edge. And if you heat it before hammering, it becomes easier to work. There is no need yet to understand atoms, crystal structures, nickel content, or metallurgy. Your hands tell you enough. This material behaves differently. The earliest known examples of worked meteoritic iron are tiny and precious rather than enormous swords or farm tools. In prehistoric Egypt, for example, people make small beads from meteoritic iron thousands of years before iron smelting becomes common. The metal is hammered into thin sheets, shaped and rolled. Think about the patience involved. There is no hardware shop selling replacement pieces. Every scrap matters. A tiny fragment of meteoritic iron may be rarer than gold in practical terms. You cannot simply decide to gather more next week. You wait for nature to deliver it, or you obtain it through exchange from someone lucky enough to possess it. So early iron is not ordinary, it is special. You do not make cooking pots from it. You do not casually turn it into nails and leave them lying around the workshop. It is more likely to become jewellery, ceremonial objects, prestige goods, or small blades associated with people of wealth and status. Oddly enough, this creates a charming reversal of the modern world. Today, iron is so common that you barely notice it. It hides inside buildings, tools, vehicles, machines, and countless everyday objects. Gold is the thing kept behind glass. In very early societies, a piece of iron may inspire more wonder than gold. Gold can sometimes be gathered from river deposits. Copper ores can be located. Meteoritic iron, meanwhile, arrives according to the deeply inconvenient delivery schedule of the solar system. No customer service department either. Your ears fill with the light ringing of hammer against metal. A craftsperson works carefully, because this material is not always cooperative. Meteoritic iron can contain structures and inclusions that make shaping difficult. Repeated hammering may cause cracks. Heating requires judgment. Too much enthusiasm can destroy what cannot easily be replaced. Slowly, however, techniques develop. Someone learns that gentle repeated blows work better than wild strikes. Someone notices that warming the metal changes how it responds. Someone discovers that polishing reveals a surface unlike stone. Knowledge accumulates quietly, perhaps without written instructions. One craftsperson watches another. A parent teaches a child. A traveller carries an object to another settlement, where local artisans stare at it and immediately begin wondering how it was made. There is probably no single moment when humanity discovers iron. That idea is tempting because modern stories love a lone inventor having one dramatic realization. You picture someone pointing at a metallic lump and announcing the beginning of the Iron Age while everyone politely applauds. History is usually less tidy. Different communities may encounter meteoritic iron independently. Different smiths may experiment with it in different ways. Some knowledge disappears, other techniques spread. A rare object travels farther than the people who originally shaped it. Scholars still argue whether certain very early iron artifacts were made from meteoritic material, or from tiny quantities of terrestrial iron produced under unusual conditions. Chemical testing has answered some cases convincingly, but not every ancient object gives up its story so easily. Corrosion complicates matters, so does contamination, and archaeologists, like all academics, can transform a small metal fragment into several decades of professional disagreement with impressive efficiency. One famous object gives you a sense of how prestigious celestial iron can become. In ancient Egypt, the burial equipment of Tutankhamun includes a dagger with an iron blade. The blade dates from long before iron becomes an ordinary material in Egypt, and scientific analysis indicates that the metal is meteoritic, with nickel and other elements matching an extraterrestrial origin. You can picture the effect it must have had. Gold surrounds the young king, precious stones gleam, elaborate craftsmanship appears everywhere, yet among those treasures rests a blade made from material that once travels through space. The object is valuable, not because iron is technologically dominant, but because it is rare. That distinction matters. You are not yet in an iron age. You're in an age when iron is an exception. People know iron exists, but knowing that a metal exists is very different from knowing how to manufacture it. A meteorite delivers metal already reduced into metallic form. Earthbound iron is usually locked inside minerals, chemically joined with oxygen and other elements. To ancient eyes, iron ore does not necessarily resemble the shining substance inside a meteorite. That creates an enormous conceptual gap. Imagine receiving a loaf of bread from the sky without ever seeing grain. You know bread exists, that you can eat it. You might even learn how to slice it beautifully, but that does not teach you farming, milling, mixing dough, or baking. Meteoritic iron gives ancient humans the finished material without revealing the recipe. Still, the material teaches important lessons. Iron can be hammered. Iron can hold an edge. Iron can be polished. Iron changes under heat. These observations become part of humanity's growing memory of materials. A curious footnote appears in the language of several ancient cultures, where expressions associated with iron sometimes seem connected with the sky or heaven. Scholars treat such linguistic evidence carefully because words shift meaning over centuries, but the possibility fits beautifully with the physical evidence. People may quite literally understand some iron as metal from above, and why wouldn't they? You see fire cross the sky. You hear a distant impact. Later, someone finds an impossible stone. Modern knowledge can make the event feel ordinary. You hear the word meteorite and immediately place it inside astronomy, geology, and chemistry. But strip those explanations away. Now you simply watch the heavens throw metal at the ground. That is rather dramatic. The strange lump passes from hand to hand. Children touch it. Elders remember the night it arrived. A craftsperson weighs it and considers what it might become. Perhaps a bead, perhaps a small blade, perhaps an ornament worn by someone whose authority is strengthened by possessing something literally connected to the heavens. No agreement has been reached on whether meteoritic iron carried the same sacred meaning everywhere it appeared. Some societies may treat it as supernatural. Others may value it mainly for rarity and appearance. In many cases, no written explanation survives at all. So you remain partly in the dark, and that darkness suits the scene. The fire is low now. A few sparks rise and disappear. The iron sits near the edge of the hearth, reflecting a dull orange glow. You do not yet know that mountains around you contain iron in quantities so enormous that future civilizations will build bridges, railways, engines, towers, and cities from it. For now, there is only this small piece, a gift of chance. Your fingers close around something colder than the evening air, something that began far beyond any landscape you know. You feel its weight resting against your palm. Around you, the settlement grows quieter. A dog shifts beside a doorway. Somewhere nearby, wood settles in the fire with a soft crack. The mystery does not need to be solved tonight. You only need to notice what your ancestors notice. This dark stone is not quite a stone. It bends beneath the hammer. It shines beneath the dust. It carries the memory of fire across the sky. And as the voices around the hearth soften, you can allow that small piece of ancient metal to remain exactly what it once was to the people holding it for the first time: rare, puzzling, useful, and almost impossibly strange. The hammer rests, the fire settles lower, the night stretches calmly above you, full of stars that no longer seem quite so distant. Your attention settles on the ground beneath your feet, not the sky now, but the earth itself. Dust, gravel, broken stone, river pebbles, red cliffs, dark streaks in exposed hillsides. The ordinary landscape begins to look slightly less ordinary once you realize that some rocks behave in ways others do not. You pick up one that feels unusually heavy. Another leaves a rusty stain on your fingers. A third seems almost black. Yet when sunlight catches a freshly broken edge, there is a dull metallic glimmer beneath the surface. None of these stones announces what it contains. There is no label, no friendly little sign saying, "useful metal hidden inside." You learn by touch, by accident, and by repeating the same small experiments until patterns emerge. Early craftspeople already live in a world of careful observation. Stoneworkers know which rocks fracture cleanly and which crumble. Potters know which clays survive firing and which explode in a kiln with enough enthusiasm to ruin everyone's afternoon. Miners learn that bright green and blue minerals can lead to copper. People working pigments know that some red and yellow earths produce vivid colours when ground into powder. So when unusual iron-rich minerals appear, they are not necessarily ignored. They are simply not understood in the way you understand them today. One common iron mineral is hematite. Its name is modern, but its appearance would be immediately familiar to ancient people. Hematite can look steel grey, reddish brown, or nearly black. Grind some varieties into powder, however, and they leave a distinctive red streak. That red colour matters. Long before anyone deliberately produces ironed metal, iron oxides are useful as pigments. Red ochre, rich in iron compounds, has been used by humans for an astonishingly long time in painting, decoration, ritual, and probably many practical purposes, so you may know iron-bearing earth first as colour. You smear it across skin, you mix it with fat or water, you apply it to stone. You notice how persistent the stain can be. Then, perhaps in another context entirely, that same kind of earth enters a fire. The transformation is subtle. You're not watching a dramatic river of molten iron pour from a furnace. The temperatures needed for that are far beyond the reach of an ordinary campfire. Instead, the mineral changes colour. Red may deepen. Black patches appear. A crust forms. Some pieces become magnetic under certain heating conditions. And that is where the ground begins behaving like a puzzle. Magnetite, another iron-rich mineral, can attract iron and can itself act as a natural magnet when magnetized. Imagine encountering that without a textbook. You place a dark stone near another small metallic object, and it seems to tug faintly. Perhaps the effect is weak. Perhaps you think your fingers moved. You try again. The attraction remains. A stone that pulls on metal feels less like geology and more like sorcery. Oddly enough, naturally magnetized pieces of magnetite, often called lodestones, eventually become important in the history of navigation. But long before anyone trusts one to help cross an ocean, someone first has to notice the very strange fact that one rock can exert an invisible pull on another object. You can almost feel the expression on that person's face. Suspicion first, then curiosity, then another experiment. Humans are wonderfully predictable. If something strange happens once, you poke it again. This habit matters enormously in early metallurgy. You do not need a theory of oxidation and reduction to notice that different stones respond differently to heat. You only need enough patience to compare them. A pottery workshop gives you excellent opportunities. The kiln becomes hotter than an open hearth. Airflow is controlled. Fuel is packed deliberately. Different minerals sometimes find their way inside, either as pigments, impurities in clay, decorative materials, or simple debris. Under intense heat, iron compounds change. Some turn darker, some react with ash, some form glassy slags. If charcoal surrounds iron, rich material and oxygen becomes limited, the chemistry begins moving in a direction that will eventually become extremely important. You do not know the word chemistry. You know that the stone came out different. Records from ancient mining regions confirm that prehistoric communities often exploited brightly coloured mineral deposits because visible colour could guide them toward useful materials. Green copper minerals are especially obvious, but red, brown, and black iron minerals also stand out once people learn where to look. The landscape slowly becomes a collection of clues. A red hill is no longer merely red. A heavy black pebble is no longer merely heavy. A rusty spring may suggest minerals underground. A dark band in exposed rock may be worth breaking open. Your senses become tools. You smell sulphur from certain ores. You feel weight in your palm. You hear a sharper ring when one stone strikes another. You watch how surfaces change beside heat. This knowledge does not arrive neatly. It accumulates in fragments. A miner notices one thing, a potter notices another, a copper smelter notices something else entirely. Then people trade stories. Perhaps someone says that a certain black stone ruins a copper batch. Someone else insists it improves it. A third person has discovered that the same stone produces an odd crust in the furnace. Nobody is holding a laboratory meeting, but the principle is familiar. Observation becomes tradition. Tradition becomes technique. And technique sometimes survives even when the original explanation is completely wrong. A curious footnote in early craft history is that ancient metalworkers may have selected ores partly by appearance, density, and furnace behavior rather than by any clear distinction between the minerals themselves. Two rocks that look similar can behave very differently under heat, while two very different looking ores may contain the same useful metal. You can imagine the frustration. You spend all day gathering what appears to be excellent ore. You crush it, you heat it, you add charcoal, you work the bellows until your shoulders complain, and the result is a miserable lump of slag. Ancient technology contains a great deal of disappointment. The successful experiments survive in stories. The failures mostly survive as rubbish heaps. Archaeologists adore the rubbish heaps. Furnace debris, slag, broken crucibles, ash, and fragments of ore can reveal more about early metallurgy than polished treasures ever could. A beautiful finished object tells you that someone succeeded. A workshop floor tells you how many strange things happened on the way. Scholars bicker over how often early encounters with iron ore were accidental byproducts of copper smelting, and how often craftspeople were deliberately experimenting with iron-rich materials for their own properties. The distinction is difficult because early furnaces are messy environments. Copper ores may contain iron. Fluxes may contain iron. Clay furnace walls contain minerals of their own. Ash contributes additional chemistry. A tiny bead of metallic iron can form without anyone having intended to make iron at all. Does that count as discovery? You can see the problem. If a craftsperson opens a furnace and finds a strange metallic speck trapped in slag, that person may notice it, ignore it, throw it away, or spend the next several days trying to reproduce it. Only the last option changes history. And even then, success is not guaranteed. The crucial obstacle is heat and atmosphere. Iron clings tightly to oxygen in its ores. To free metallic iron, you need conditions that encourage carbon monoxide and carbon from charcoal to remove that oxygen. This can happen below iron's melting point. That is fortunate, because ancient furnaces cannot initially reach the temperatures required to melt pure iron. But the process is finicky. Too much air and the iron oxidizes. Too little heat and almost nothing happens. Poor charcoal gives weak temperatures. Large ore pieces heat unevenly. Wet fuel wastes energy. A furnace wall may crack. Bellows may fail. Wind may shift. You begin to appreciate why discovering iron is less like finding a recipe and more like trying to persuade several stubborn natural processes to cooperate at once. Your hands become black with charcoal dust. You crouch beside a low furnace or kiln. Heat presses against your face. The leather or skin bellows creak rhythmically. Each push forces air into glowing fuel. The charcoal brightens. Orange turns nearly white in the hottest places. You cannot look directly for long. There is a dry mineral smell, mixed with smoke and heated clay. Then the ore begins changing. At first, nothing seems dramatic. The rock does not suddenly become a sword. Instead, small chemical transformations occur inside the furnace. Oxygen leaves certain compounds. Minerals soften. Silica and other impurities begin combining into slag. Tiny metallic particles may appear. If conditions are right, those particles can gather. But that phrase, "if conditions are right," hides generations of experience. How much charcoal? How much ore? How strong should the airflow be? When should the charge be added? How long should the firing continue? What size should the furnace be? Which stones are worth using? A council decree will not save you here. Your teacher is the fire, and the fire is not especially patient. Some communities become expert at reading furnace colour. Others judge temperature from sparks, sound, flame, or the behaviour of the charge. None of these methods provides a number in degrees. You read heat the way a sailor reads weather. Experience sits in the body. You know when to pump harder. You know when the fuel bed is collapsing. You know when the flame looks wrong. You know that one particular ore from one particular hillside behaves better than a similar-looking ore from somewhere else. This local knowledge can become incredibly specific. A deposit may be roasted before smelting. Roasting means heating ore in air before the main furnace process. It can drive away moisture, alter minerals, make rock easier to crush, and remove certain unwanted substances. Again, nobody needs to understand the chemistry perfectly. You notice that roasted ore works better, so you roast it. The practice becomes part of the craft. People crush ore into smaller pieces because smaller fragments heat more evenly. They sort out obvious waste rock. They wash material. They combine ores. They adjust charcoal. Every improvement moves you closer to deliberate control. There is no single magical stone that teaches humanity ironworking. There is instead a growing familiarity with a family of difficult materials: red ochre, brown limonite, dark magnetite, dense hematite. Each offers clues. Some are easy to recognize, some are richer, some smelt more readily, some are troublesome. The earth seems to contain metal everywhere, yet it refuses to hand it over politely. For a moment, it feels as though the hillside itself is testing you. You run your thumb across a freshly broken mineral surface. Dust settles into the lines of your skin. The stone is cool now, harmless and silent. But once placed among charcoal and driven by air, it becomes part of something more complicated. Colour shifts, texture changes, weight changes. The furnace produces materials that did not seem to exist before. That is the important realization. Stone is not fixed. Heat can transform it. Air can transform it. Fuel can transform it. And if one kind of rock can yield copper, perhaps another can yield something else. You do not yet have certainty. You have clues. A red streak on a grinding stone. A black mineral that pulls faintly at metal. A dense rock that behaves strangely in a kiln. A glassy lump in the ash. A tiny metallic glint buried where no one expected it. Nothing announces itself as the beginning of a technological revolution. It simply looks curious, and curiosity is enough. The furnace roars hotter than anyone around it expected. You're standing close enough to feel the heat push against your cheeks, while charcoal snaps and shifts inside a clay chamber. Someone works the bellows steadily. Another person feeds fuel through the opening. A third watches the colour of the flame with the concentration of someone who has learned, through a repeated inconvenience, that the fire has moods. This furnace was not necessarily built for iron. That is the important part. It may have been intended for copper, perhaps for firing pottery, perhaps for experimenting with mineral mixtures already familiar to local craftspeople. Yet somewhere inside that glowing chamber, an iron-rich stone is exposed to exactly the right combination of heat, charcoal, and limited oxygen. Something unexpected begins to happen. Not melting, not yet. Instead, the mineral starts losing oxygen. The iron locked inside the stone slowly changes into tiny particles of metal. You would not see this transformation clearly from outside. There is no bright stream pouring into a mould. There is no theatrical moment when everyone gasps and declares a new age. The furnace simply continues to burn. Inside, however, chemistry is quietly rearranging the world. Ancient metal workers already know that certain ores can become copper under intense heat. They know that charcoal does more than provide warmth. They know that blowing air into the fuel raises the temperature dramatically. What they do not know in modern terms is why some minerals surrender their metal while iron remains stubborn. Iron oxide holds on tightly to oxygen. To release the iron, the furnace atmosphere must become reducing. That sounds technical, but the practical idea is wonderfully simple. The charcoal burns. Carbon reacts with oxygen. Carbon monoxide forms. That carbon monoxide passes through the hot iron ore and pulls oxygen away from the iron compounds. What remains can become metallic iron. Nobody standing beside the furnace needs to know the words carbon monoxide. They only need to notice that one kind of firing produces a result that another does not. That distinction is the beginning of control. Your eyes water as smoke curls through the workshop. The air tastes dusty. There is the dry smell of hot clay, ash, charcoal, and roasted mineral. Someone opens a small vent. The flame changes colour. Someone else pumps the bellows harder. The temperature rises. A furnace like this might reach around 1,000 degrees Celsius, perhaps somewhat higher in favourable conditions. That is hot enough to reduce some iron ore. It is still not hot enough to melt pure iron, which requires a temperature above 1,500 degrees Celsius. This difference explains why the first iron is so confusing. Copper smelting teaches craftspeople to expect liquid metal. Copper melts at a much lower temperature. Once produced, it can collect as molten metal and be poured or shaped. Iron refuses to cooperate in that familiar way. Instead of becoming a neat pool, it appears as a spongy, dirty mass of metal particles tangled with slag. If you're expecting liquid metal, the result may look like a failed furnace batch. Imagine the disappointment. Hours of fuel, hours of bellows work, a great deal of smoke. Then, when the furnace cools enough to inspect, you find an ugly black lump that looks like something the fire itself tried to spit out. You could throw it away. Someone probably does. But eventually, someone hits it. That decision matters. The strange lump does not shatter entirely, some part of it flattens. The slag cracks. A metallic surface appears beneath the crust. You strike again. More brittle material breaks away. The core behaves differently from stone. Now the failed batch becomes interesting. Records confirm that early iron production often creates solid masses rather than molten iron, and these masses require hammering while hot to consolidate the metal and remove trapped slag. To an early craftsperson, however, this would be learned through sensation rather than written instruction. The hammer gives feedback. Stone feels one way. Slag feels another. Metal answers with a different sound. You listen. Clang. Crack. Clang. A reddish spark jumps away. You turn the mass with tongs. Another blow compresses it. Under repeated hammering, the object becomes denser. The idea forms gradually. The furnace has not simply changed the colour of the ore, it has produced something new. But was the first useful iron produced by accident? Historians still argue whether early iron smelting emerges mainly from accidental experiments inside copper smelting traditions, or through more deliberate attempts to reproduce the properties of known iron metal. There is no single surviving workshop where someone kindly leaves a clay tablet saying, "Today we discovered terrestrial iron by mistake." Archaeology rarely offers such considerate paperwork. Instead, scholars examine furnace remains, slag composition, ore sources, tools, and the chronology of early iron objects. The evidence suggests long periods of experimentation. This makes sense. One accidental success is not enough. Suppose your furnace produces metallic lump today. Tomorrow you repeat the firing and get nothing useful. Was the ore different? Was the charcoal damp? Did the bellows push too much air? Was the furnace hotter yesterday? Did someone unknowingly mix in a different mineral? You have dozens of variables and no thermometer. Reproducing the results may require years of trial and error. One scandalous aside from the history of technology is that many inventions probably spend long periods being rediscovered, forgotten, and rediscovered again because early techniques are difficult to reproduce reliably. A successful result does not instantly become a stable industry. Knowledge has to become repeatable. That is much harder. Your workshop begins treating the furnace differently. You notice that charcoal works better than raw wood. Charcoal is lighter, cleaner burning, and capable of producing intense heat when supplied with enough air. You notice that small ore fragments behave more consistently than large chunks. You notice that placing ore among deep layers of charcoal changes the outcome. Perhaps you also notice that restricting air in certain parts of the furnace helps metallic iron survive instead of immediately combining with oxygen again. The furnace itself may begin changing shape. An ordinary hearth is too open. A deeper chamber holds heat better. Clay walls concentrate the temperature. A narrow opening controls the draft. A tuyere, a ceramic or clay pipe carrying air from bellows into the furnace, allows the air blast to enter exactly where it is needed. Now the glowing zone becomes hotter and more focused. You lean close and hear the bellows breathing, in, out, in, out. The rhythm becomes part of the craft. Too weak, and the furnace cools. Too strong, and fuel burns too quickly, or conditions become excessively oxidizing in the wrong place. The person operating the bellows is not merely performing labor. That person is controlling the furnace atmosphere with every movement. Experience becomes almost musical. A skilled worker recognizes the correct rhythm. Another watches sparks. Someone else feeds charcoal at measured intervals. This is no longer random fire. It is managed fire. A curious footnote appears when you consider how much early metallurgy depends on ordinary craft traditions that seem unrelated. Potters contribute knowledge of heat-resistant clay. Charcoal makers contribute fuel expertise. Miners understand ore deposits. Stoneworkers know crushing and sorting. Metalsmiths understand hammering. Leather workers may make bellows. Iron does not emerge from one isolated genius. It emerges from a network of practical knowledge. Even the furnace walls participate. Clay linings can react chemically with slag. Different clays withstand heat differently. Some crack quickly, others vitrify, becoming partly glassy. A furnace may work beautifully once and collapse during the next firing. You rebuild, you adjust thickness, you alter openings. You discover that technology often advances by repairing something that went wrong. There is no shame in this. Most workshops are probably held together by experience, patches, and mild irritation. The ore itself is also prepared more deliberately. You roast it in an open fire. The stones change colour and become easier to break. Then you crush them. A hammerstone rises and falls. Chunks become gravel. Gravel becomes smaller pieces. You sort away obvious waste. The better material goes into the furnace. Roasting can remove water and change some iron compounds into forms that respond more predictably during smelting. Again, you do not need the explanation, you need the result. The roasted ore gives better metal, so the method survives. Slowly. Experimentation becomes procedure. First charcoal, then ore, more charcoal, air through the tuyere, heat, patience. Watch the flame. Listen to the furnace, add fuel, maintain the charge. The process may continue for hours. At some point, slag begins to soften and move. Depending on furnace design, it may collect at the bottom or even be tapped out through an opening. The iron particles remain solid. They stick together gradually into a mass. When the firing ends, you face another problem. How do you retrieve it? One method is to dismantle part of the furnace. Clay is broken away. Heat rolls outward. Someone reaches in with long tools. The mass is dragged free. It glows orange-red in the evening air. For the first time, you can see what the furnace has created. It is ugly. That cannot be emphasized enough. The earliest iron product is not a polished sword blade. It resembles a scorched sponge filled with dirt. Slag clings to it. Charcoal fragments are trapped inside. Some areas contain useful metal. Others may be barely reduced ore. If a modern customer received this object after ordering iron, there would be a complaint. To an ancient smith, it is possibility. You place it on a stone or metal anvil. The first hammer strikes and sparks and fragments outward. The hot slag squeezes from cracks. You fold or turn the mass, strike again. The shape becomes tighter. Metallic regions begin welding together under the combined effect of heat and pressure. The object becomes increasingly coherent. A council decree proves nothing here. No king can command the chemistry to behave. Authority belongs to whoever understands the furnace well enough to make it work. That gives metalworkers a peculiar kind of status. Their craft looks almost supernatural from outside. They take red or black stone, they bury it in fire, they breathe air into the furnace through artificial lungs, then they pull out metal. To anyone unfamiliar with the process, the transformation must feel astonishing. Yet the craftsperson knows it is less magical than exhausting. Charcoal must be made in huge quantities, or must be mined. Clay must be prepared. Bellows must be maintained. Furnaces must be rebuilt. One successful bloom can represent days of preparation. And still, some firings fail. That uncertainty makes every good result valuable. You begin saving the successful conditions in memory. This ore from that hillside, this much roasting, this furnace height, this charcoal, this bellows rhythm, this firing time. Gradually, a repeatable method takes shape. Not perfect, not efficient, but reliable enough that iron can be produced intentionally. The accidental experiment has become a craft. The furnace glows more quietly now. Its walls radiate warmth into the darkness. A worker scrapes slag from the floor. Another turns the compacted metal with tongs, examining the surface. Nothing about the object is graceful yet. It is rough, blackened, scarred, and heavy. But it did not fall from the heavens. It came from stone. That difference changes everything. You can return to the hillside. You can gather more ore. You can make more charcoal. You can build another furnace. For the first time, iron is no longer limited by luck. It has become something human hands can attempt to make. You begin to understand that iron has an attitude. Copper is demanding, certainly. Bronze requires planning, trade, and careful proportions. But iron seems almost personally offended by the idea that humans should control it. You feed the furnace with charcoal. You push air through the tuyere. You watch the interior brighten from orange to yellow. Still, the iron does not melt. This is one of the most important difficulties in the entire history of metallurgy. Pure iron melts at a temperature above 1500 degrees Celsius, far beyond what the earliest small furnaces can usually achieve. Copper melts at a little above 1000 degrees Celsius, and many copper ores can be smelted under conditions that early craftspeople learned to produce relatively reliably. Iron demands more, not simply more heat either. That is where the problem becomes interesting. You could make a very hot fire and still produce poor iron if the chemical conditions inside the furnace are wrong. Heat alone is not enough. Air alone is not enough. Charcoal alone is not enough. The furnace must balance all three. You crouch beside the opening and feel the blast from the bellows enter through the clay nozzle. The charcoal near the tuyere glows fiercely. Farther up, the temperature drops. Different regions inside the furnace are performing different tasks at the same time. Ore descends, hot gases rise, charcoal burns, iron oxides lose oxygen, slag softens, metal particles begin to gather. The furnace is not simply a container for fire, it is a vertical landscape. A few centimetres can make the difference between useful reduction and disappointing waste. Records confirm that early bloomery iron was commonly produced below the melting point of iron, with metallic particles forming in a solid or semi-solid state rather than as a pool of liquid metal. That fact explains a great deal about early ironworking. If the metal will not melt, you cannot simply pour it into a mould the way you might cast bronze. You must work with a solid mass. This changes everything. The shape of the furnace matters, the timing matters, the location of the hottest zone matters, the amount of charcoal matters. Even the size of the ore pieces matters because each fragment must be heated thoroughly enough for chemical reduction to occur. You discover that increasing the air blast makes the fire hotter. Wonderful! So perhaps you pump harder. The bellows groan. Air rushes through the tuya. Charcoal flares brilliantly. The furnace becomes hotter. Surely more heat must mean more iron. Not necessarily. Too much oxygen can create conditions that encourage newly formed iron to oxidize again. You can actually undo part of your own success. There is a sleepy kind of cruelty in that. You work harder, and the furnace becomes less cooperative. The lesson is subtle. A good iron furnace does not simply burn as fiercely as possible. It must burn correctly. The charcoal creates both heat and the reducing gases needed to separate oxygen from iron compounds. If you allow ordinary air to dominate everywhere, the chemistry moves in the wrong direction. So you learn to control the blast. Not with gauges, not with digital displays, with experience. The colour of the flame tells you something. The sound tells you something. The way charcoal settles tells you something. The appearance of slag tells you something else. Your senses become instruments. The bellows rhythm changes. Long pushes, short pauses. Another push. Someone watches the furnace mouth. Another person listens for changes in draft. A skilled smelter may notice trouble long before anyone else understands why. This is knowledge built into habit. You do not calculate oxygen concentration. You recognize the furnace's personality. One day it draws well. Another day the wind works against you. A damp batch of charcoal produces weak heat. A cracked wall leaks air. A tier becomes partly blocked by slag. A careless charge causes ore to descend too quickly. Each problem teaches another lesson. The furnace may look primitive to modern eyes, but operating it well requires impressive judgment. Oddly enough, charcoal itself is a technology. It is not simply burned wood gathered from the ground. To make good charcoal, wood is heated with limited access to oxygen. Much of the water and volatile material is driven away, leaving a carbon-rich fuel that burns hotter and more predictably than ordinary wood. That means your iron workshop depends on another skilled craft entirely. You need charcoal makers. They stack wood carefully. They cover it with soil, turf, or another material. They control small openings. They prevent the entire pile from simply becoming a bonfire. Too much oxygen and the wood burns away. Too little heat and the conversion is incomplete. A successful charcoal burn can take patience and close attention. When you finally receive the fuel, it feels almost weightless. Black pieces leave dust on your fingertips. They snap easily. They also contain the stored work of the forest. Iron production consumes an enormous amount of fuel. A furnace that looks modest can devour baskets of charcoal. That creates practical limits. You cannot place iron production anywhere you like. You need access to ore. You need water for people and other crafts. You need clay or stone suitable for furnace construction. Most of all, you need woodlands. A landscape begins feeding the furnace. Trees are cut, wood is dried, charcoal is made, fuel is transported, ore is mined and crushed. The amount of preparation behind a single iron object can be astonishing. A knife begins as a forest and a hillside. You might consider that while holding one. The relationship between fuel and furnace design becomes increasingly important. A taller shaft lets hot gases travel upward through descending ore and charcoal. This can preheat the charge before it reaches the hottest zone. You gain efficiency. The furnace uses heat that would otherwise escape. But height also creates complications. If the shaft is too narrow, material can jam. If it is too wide, the air blast may not penetrate evenly. If the walls are poorly built, they may crack. If the charge descends irregularly, the chemical conditions become unpredictable. So you adjust, you rebuild, you experiment with clay mixtures. You may add organic material to the clay to reduce cracking. You may make the wall thicker in one place and thinner in another. A curious footnote from experimental archaeology is that modern researchers trying to reproduce ancient smelting techniques sometimes discover just how unforgiving these furnaces are. Even when they understand the chemistry perfectly, they can still produce disappointing results because knowledge written on paper does not automatically become skill in the hands. That would probably amuse an ancient smelter. You arrive with modern science. The furnace replies with slag. The difficulty lies partly in temperature control. You cannot measure the furnace numerically, so you infer heat from visible clues: dull red, bright red, orange, yellow, near white. These colours become a rough thermometer, but daylight can make them difficult to judge. Smoke obscures the interior. Different materials glow differently. Your own eyes tire, so other clues matter. The fluidity of slag is one. When slag begins to soften and move, the furnace has entered an important range. Slag is not merely garbage. It helps separate unwanted minerals from the metallic iron. Iron ore contains more than iron oxide, silica, clay, stone fragments, and other materials enter the furnace. Some of these combine into molten or semi-molten slag. If the slag becomes fluid enough, it can move away from the growing iron mass. If it remains too viscous, it traps metal. If conditions become excessively hot in certain ways, other unwanted reactions may occur. The smelter is balanced in a furnace full of compromises. Scholars bicker over exactly how quickly early ironworkers developed deliberate control over slag chemistry, rather than relying mainly on favourable local ores and accumulated practical experience. The answer probably varies from place to place. Some ore deposits naturally contain components that encourage useful slag formation. Elsewhere, craftspeople may deliberately add materials. The archaeological record does not always reveal whether an addition was intentional, habitual, or simply part of the ore. Even so, the pattern is clear. Successful iron-making becomes increasingly controlled. You stop treating the furnace as a place where ore is simply heated. You begin treating every ingredient as part of a system. Charcoal determines temperature and atmosphere. Air determines combustion. Ore determines how easily iron can be freed. Furnace geometry determines where reactions occur. Slag influences how well the metal separates from waste. All of these things interact. You change one, and several others respond. Perhaps the most confusing discovery involves carbon. Iron in contact with charcoal can absorb carbon under certain conditions. A small amount can make iron harder. Too much changes its properties more dramatically. At very high carbon levels, the metal can melt at a lower temperature than pure iron. This eventually becomes crucial in later iron technology, but for an early smelter it creates another layer of unpredictability. Different parts of the same mass may contain different amounts of carbon. One section bends easily, another is harder, another cracks. The lump pulled from the furnace is not necessarily uniform. You cannot assume that iron is simply iron. Its behaviour depends on how it was made. That realization takes time. You heat a piece, hammer it, cool it, sharpen it, test the edge. Sometimes it performs beautifully. Sometimes it bends. Sometimes it refuses to cooperate. You begin sorting metal by behaviour. The best material may be reserved for cutting edges. Softer material may suit other purposes. No chemical chart hangs on the workshop wall. Your hammer tells you what you have. There is another obstacle. Every time you reheat iron for forging, you expose it to oxygen. A layer of scale forms on the surface. Tiny amounts of metal are lost. Repeated heating and hammering gradually consume part of the original bloom. You begin with a large ugly mass and finish with something surprisingly small. The finished tool hides the waste behind it. This is one reason iron objects demand so much labour. The smelter wrestles metal from ore. The smith then wrestles useful iron from the smelter's imperfect product. A council decree proves that some later states regulate metal workers, mines, fuel, and production, but no decree can remove the fundamental physical difficulty. Iron still requires skill. You feel it in the workshop. The heat is dry and relentless. The floor is gritty beneath your sandals. A bellows handle grows smooth from repeated use. The iron on the anvil glows orange for only a short time before fading toward red. You must strike while the temperature is right. Too cold, and the metal resists. Too hot, and you may damage it. Again, the craft lives inside a narrow range. Control becomes the real invention, not simply discovering that iron exists, not simply discovering that ore can produce it. The deeper breakthrough is learning how to repeat the transformation deliberately. You regulate air, you prepare fuel, you select ore, you build the furnace carefully, you watch, you listen, you make small adjustments that outsiders may barely notice. The fire still looks wild, but it is no longer uncontrolled. Inside that clay chamber, humans are beginning to manage a chemical environment they cannot see. The iron never needs to become liquid. That once seems like a failure. Instead, it becomes the foundation of an entire method. The stubborn metal remains solid, glowing quietly among the charcoal, while human patience closes the distance between stone and tool. You stand beside a furnace that looks, at first glance, almost too simple to change the course of human history. It is a clay shaft rising from the ground, darkened by smoke and repeated firing. Charcoal waits nearby in baskets. Crushed ore sits in another pile. A pair of bellows rests beside the tuyere, the narrow pipe that carries air into the hottest part of the furnace. Nothing here looks grand. There are no towering chimneys, no rivers of molten metal, no machinery, just earth, fuel, stone, air, and human patience. Yet this compact furnace contains the central trick of early iron making. It does not melt iron, it grows it. The process begins slowly. A fire is lit inside the furnace and allowed to warm the walls. This matters because a cold furnace steals heat from the charge. Moisture inside clay can also become troublesome if heating happens too quickly. So you wait. The interior darkens, then glows. Charcoal settles. The furnace begins to breathe. Someone works the bellows and sends repeated bursts of air through the tuyere. The fuel near the air inlet brightens sharply. Heat climbs through the shaft. Once the furnace is hot enough, ore and charcoal are added in alternating charges. A basket of charcoal, a measured quantity of crushed ore, more charcoal, then more ore. You watch the material disappear into the furnace mouth, sinking gradually as the fuel burns beneath it. Inside, the real work occurs invisibly. Hot gases rise through the descending ore. Iron compounds begin losing oxygen. Particles of metallic iron form. They do not become liquid droplets that gather neatly at the bottom. Instead, they remain solid, or nearly solid, soft enough at high temperature to stick together. Tiny particles become larger clusters. Those clusters join others, slowly, over hours. A spongy mass develops near the hottest zone. This mass is called a bloom. The name suits it surprisingly well. The iron seems to grow inside the furnace. Not gracefully, perhaps. It does not resemble a flower unless your flowers are black. Lumpy, full of slag, and capable of ruining a sandal. But the principle is similar. Something gradually takes shape. Records confirm that bloomery furnaces can produce iron without ever reaching the melting point of pure iron. Instead, solid metallic particles gather, while liquid or softened slag moves around and through them. This is the defining feature of the bloomery process. You're not casting metal, you're separating it. That distinction becomes easier to understand when you imagine what is happening between individual grains of ore. A piece of iron oxide enters the hotter part of the furnace. Carbon monoxide produced by burning charcoal reacts with it. Oxygen's removed. Metallic iron remains. At the same time, unwanted mineral material begins combining into slag, silica, iron oxide, ash, and other compounds form a dark, glassy substance that can soften enough to flow. Some slag collects below the bloom. Some remains trapped inside it. The growing iron mass resembles a metallic sponge because it contains cavities, slag pockets, and charcoal fragments. It is anything but finished. Yet it is the prize. The smelter's task is to create conditions that encourage iron to remain in the bloom while slag separates as much as possible. You listen to the furnace. The bellows pulse steadily. The air blast produces a low roar. Charcoal shifts with soft collapsing sounds inside the shaft. Occasionally sparks escape from the top. The furnace mouth glows. A worker adds another charge. The timing becomes rhythmic. There is no clock, but there is routine. The people operating the furnace may judge progress by the height of the charge, the colour of the interior, the amount of fuel consumed, the behaviour of slag, and simply by experience. Hours pass. A bloomery firing can require constant attention. You cannot light it and wander away for lunch. The furnace is a needy little creature. It must be fed, it must be watched, it must be supplied with air. If the bellows stop for too long, the temperature drops. If fuel runs low, the reaction slows. If slag blocks the tuyere, airflow suffers. If too much material accumulates in the wrong place, the furnace may choke, so the crew works continuously. This makes iron smelting social. Several people may be needed just to keep the process moving efficiently. One works the bellows, another prepares charcoal, another breaks and sorts ore, another watches the furnace. Tasks rotate because pumping bellows for hours can turn your shoulders into a formal complaint against metallurgy. Oddly enough, experimental smelters using reconstructed bloomery furnaces often discover that the bellows operator becomes one of the most important people at the site. A beautiful furnace and excellent ore still accomplish very little if the air supply is inconsistent. The bellows are lungs. Without breath, the furnace cools. Different bellows designs can provide that breath. Some are made from animal skins. Others use wooden chambers or flexible membranes. They may be operated by hand or foot. The exact design varies across regions and periods. What matters is the controlled blast. Air enters through the tuyere and strikes the charcoal. That zone becomes intensely hot. The tuyere itself must survive these conditions. Clay protects it, but repeated firing can damage the tip. You may pull away a broken fragment and replace it. Another inconvenience. Another piece of knowledge. The location of the tuyere also influences where the bloom forms, too high or too low, and the furnace behaves differently. The angle of the air blast changes fuel consumption and temperature distribution. A few small construction choices can dramatically alter the outcome. This is why two furnaces that look nearly identical from the outside may perform very differently. There is craftsmanship in the geometry. As the firing continues, slag begins accumulating. Some bloomery furnaces are designed so slag remains in a pit beneath the active zone. Others allow it to be tapped through a small opening. If you tap slag, you pierce or open the furnace wall and let the hot material run out. It emerges glowing, thick, and dark. For a brief moment, the workshop has something that resembles molten lava moving across the ground. Everyone nearby gives it proper respect. It may flow into a shallow channel. It may collect in a pit. It cools into glassy or rope-like shapes. Archaeologists later find these forms and use them as clues to reconstruct how the furnace operated. A curious footnote is that slag heaps can sometimes reveal ancient production on a scale that surviving iron objects cannot. Iron rusts and disappears. Slag is stubborn, A village may lose nearly every tool it once used, yet leave behind a mountain of industrial waste, saying, rather impolitely, "Yes, we were here, inside the furnace. The bloom keeps growing. It may weigh only a few kilograms, or considerably more depending on the furnace, ore, and skill of the smelters. Bigger is not always better. A very large bloom can be difficult to extract and consolidate. A small one may represent poor yield. The ideal size depends on what the workshop can handle. You also need enough metallic iron inside it to justify the effort. Iron recovery from early smelting can be inefficient. Some iron stays behind in slag. Some remains unreduced. Some is lost during later hammering. That means a large quantity of ore can produce a surprisingly modest amount of usable metal. The waste is part of the process. Eventually, the smelter decides the bloom is ready. This judgment is not obvious. You cannot see it clearly through the furnace wall. Perhaps the firing has lasted the expected number of fuel cycles. Perhaps slag behavior suggests the reaction is complete. Perhaps experience says the mass has reached the right size. Whatever the signal, feeding stops. The furnace is allowed to settle. Now comes the dramatic part. The bloom must be removed while still hot enough to work. Depending on furnace design, part of the clay wall may be broken open. You hear the crack of tools against fired clay. A section collapses. Heat rushes outward. The interior appears almost painfully bright. Someone reaches in with hooks or tongs. The bloom resists. It may be stuck to slag. It may cling to the furnace floor. It may be larger than expected. Several people pull. The mass finally comes free. It lands on the ground with a dull, heavy sound. There it is. Fresh iron from ore. Not beautiful, not clean, not shaped, but real. The surface is black and rough. Sections glow orange. Slag drips from openings. Charcoal clings to it. The bloom looks almost alive while hot, with brighter patches appearing as it turns. There is little time for admiration. The next task begins immediately. You move the bloom to an anvil, stone, or heavy working surface. A hammer rises. The first strike sends fragments flying. Slag breaks away. Another strike compresses the iron. Then another. The spongy structure begins closing. Pockets collapse. Metal particles weld more firmly together. Slag is squeezed toward the surface. This initial compacting is sometimes called bloom consolidation. It is one of the most physically demanding moments in the process. The bloom is awkward. Its composition is uneven. It cools rapidly. You may need to return it to a hearth for reheating, then a hammer again. Heat, strike, turn, strike, reheat. The operation slowly transforms something resembling burned rubble into a coherent piece of metal. No agreement has been reached on exactly how standardized bloomery procedures were within many early communities. Some scholars emphasize highly specialized craftspeople with carefully transmitted techniques. Others point to considerable local variation, with different furnaces, ores, and working traditions producing successful iron in different ways. The archaeological evidence supports diversity. There is no single universal bloomery. Some furnaces are shallow, some are tall, some are partly buried, some are freestanding, some tap slag, some do not. Different societies solve the same metallurgical problem in their own ways. That flexibility helps ironworking spread. You do not need to copy one furnace perfectly. You need to understand what the furnace must achieve. Enough heat, a reducing atmosphere, contact between ore and charcoal, a way to manage slag, a way to recover the bloom. Everything else can be adapted under the local landscape provides the materials. Clay from a riverbank, stone from nearby ground, wood from surrounding forests, or from a hill, animal hide for bellows. Iron-making becomes possible wherever people can combine these resources with sufficient skill. That does not make it easy. The furnace floor tells the truth. Broken tuya pieces, charcoal dust, rejected ore, failed slag, fragments of furnace wall, bits of iron accidentally lost during hammering. Success sits in the middle of an impressive mess. You lift a newly compacted piece with tongs. It is smaller now, denser, more recognizably metallic. The surface still carries scars and dark scale. But the material no longer looks like ore. It bends beneath the hammer rather than crumbling. It can be reheated. It can be divided. It can be shaped. The furnace has completed the first great transformation. Stone enters from above. Metal leaves through the broken wall. The bloomery does not conquer iron by melting it. It persuades countless tiny particles to gather together, then leaves human hands to finish the job. The charcoal settles into ash. The bellows fall silent. Heat still radiates from the furnace wall while the compacted iron rests nearby. It is rough, heavy, imperfect, and full of work still waiting to be done. But for the first time, the furnace has given you enough metal to begin shaping and tension itself. The iron on the anvil does not yet look like something you would trust with an important job. It is rough, uneven, streaked with dark slag, and full of small cavities. One edge is thick, another looks cracked. The whole piece seems to contain more uncertainty than metal. You lift the hammer anyway. The iron glows a deep orange. The first strike lands with a heavy ringing sound. A scale of black material jumps away. You turn the piece with tongs and strike again. This is where iron begins to become useful. Smelting produces the metal, but forging teaches it manners. A freshly consolidated bloom can contain pockets of slag, partially welded areas, and regions that behave differently under the hammer. To turn that material into something dependable, you need repeated cycles of heating, hammering, folding, cutting, and welding. The work is physical. It is also surprisingly delicate. If the iron cools too much, it becomes harder to shape and may crack under careless blows. If you overheat it, parts of the surface can burn or oxidize badly. A skilled smith learns to judge temperature from color: bright yellow, orange, red, dark red, then too cold. You do not count degrees. You watch the glow. In a dim workshop, the iron tells you its temperature in light. You place the piece back into the charcoal hearth. A bellows sends air beneath the fuel. The coals brighten. Heat wraps around the iron. You wait. Then the tongs pull it free again. Hammering resumes. Records confirm that bloomery iron often requires extensive secondary working to remove slag and weld separate metallic regions into a more uniform bar. That means the hammer is doing more than changing shape. It is improving the material itself. When you strike hot iron, trapped slag can squeeze outward. Small voids close. Metal surfaces press together. Under enough heat and pressure, clean iron surfaces can weld without melting. This ability is crucial. Iron can be joined to iron in the forge. You do not need to melt the entire object. Instead, you heat two surfaces until they are dangerously hot, bring them together, and hammer them until they become one. The technique is called forge welding. To modernize, it almost looks impossible. Two solid pieces become a single piece under the hammer, but the metal does not think in the tidy categories you learned in school. At the right temperature, clean surfaces can bond. You discover this through practice. Perhaps a bar splits. Perhaps you deliberately fold a piece back on itself. Perhaps two fragments are placed together simply because metal is too valuable to waste. The joint survives. That becomes knowledge. Soon, a smith can combine pieces, repair flaws, build larger shapes, and arrange different qualities of iron within the same object. Your hammer falls in rhythm: clang, turn, clang, reheat, clang. The workshop develops its own music. There may be more than one hammer. A master smith holds the hot piece and directs the work. An assistant swings a heavier sledge. The master taps a location lightly. The assistant understands. Strike here. Another tap. Now there. This system allows powerful blows to land with precision. You can imagine the trust required. One person's fingers are holding the tongs only a short distance from where another person is bringing down a heavy hammer. A bad day at the forge is not improved by poor communication. Oddly enough, some blacksmithing traditions develop elaborate rhythms between the smith and striker, almost like percussion. The pattern of blows can communicate when to strike, when to stop, and where force is needed. Metalwork becomes partly audible knowledge. A visitor might hear only noise. The smith hears instructions. As slag is expelled, the iron becomes cleaner. You may cut the mass into smaller sections. A chisel is placed against the hot bar. The hammer drives it downward. The iron separates. Now each portion can be worked more thoroughly. You flatten one, fold it, reheat it, hammer the layers together, repeat. This does not mean every ancient iron object is endlessly folded in the dramatic way modern storytelling sometimes suggests, but repeated working can help distribute remaining slag and consolidate an inconsistent bloom. The point is not spectacle, the point is reliability. Early iron can vary even within one bar. One region may be soft and nearly pure iron, another may contain more carbon. One may hold elongated slag inclusions, another may be cleaner. The smith learns to notice these differences through behaviour. A harder region resists the hammer slightly differently. A brittle area may crack, a soft area spreads easily. You cannot see carbon atoms. You feel consequences. Your hands become a testing laboratory. The hammer becomes a measuring instrument. You begin to select metal according to purpose. Soft. Low-carbon iron is easy to shape. It bends rather than snapping suddenly. That makes it useful for many objects. Hooks, nails, clamps, chains, rivets, simple tools, fittings for wood, agricultural implements. A cutting edge, however, asks for something better. If the iron is too soft, the edge dulls quickly. So the smith starts paying attention to pieces that harden more effectively. This introduces one of the most important lessons in ironworking. Not all iron is equal. The ore matters. The furnace matters. The position inside the furnace matters. The charcoal contact matters. The reheating matters. The cooling matters. Two bars that look similar can perform very differently. A curious footnote appears in the way ancient smiths may identify these differences without formal chemistry. Sparks produced during grinding or striking, fracture appearance, hardness under a file or stone, and the way metal responds during forging can all provide clues. The smith develops categories based on behaviour: good edge metal, soft iron, brittle iron, easy welding iron, difficult iron. These names may vary, but the practical distinctions are real. You are building a science without equations. Trial becomes memory. Memory becomes craft tradition. A young apprentice watches where the master places the iron in the hearth. Why not deeper? Because that part becomes too hot. Why turn it now? Because one side is heating faster. Why use a smaller hammer here? Because the shape is nearly finished. The apprentice may ask fewer questions than you expect. Much of craft knowledge is demonstrated rather than explained. Stand here, watch, listen, try. Do it again. No one has written a handbook titled Convenient Methods for Persuading Uncooperative Iron. Your teacher may simply sigh when you ruin a piece. That is also education. Scholars bicker over how specialised the earliest smiths were, and whether ironworking was initially controlled by small elite groups or practiced more broadly in some regions. The answer likely differs from place to place. Some communities may have had dedicated smiths whose knowledge was guarded carefully. Others may have combined ironworking with copper working, farming, or other seasonal crafts. What seems clear is that good forging requires enough repetition to create expertise. A person who shapes iron occasionally will not read the metal as quickly as someone who spends years beside the hearth, and iron rewards experience. Consider something as simple as making a knife. You begin with a bar, heat it, hammer one end thinner, draw the metal outward, turn it, correct the bend, flatten the spine, shape the point, reheat, refine. The blade gradually appears, not because metal is removed, as when shaping stone, but because the same material is redistributed. A thick section becomes long and thin. A square bar becomes flat. A blunt end becomes tapered. Forging allows you to move metal almost like very stubborn clay. Very hot, extremely heavy clay that can burn through your sandals. But clay in principle. The blade still needs finishing. Hammer marks remain. The edge is uneven. Scale covers the surface. You scrape or grind it with abrasive stone. The shape becomes cleaner. The edge becomes sharper. Polishing may follow. The finished knife looks simple. Its simplicity hides dozens of judgments. Where to strike? How hard? At what temperature? How often to reheat? How thin the edge can become without failing. The same is true for an axe, a hoe, a chisel, a sickle, a spearhead. Each object creates new forging problems. An axe needs an opening for a handle. One solution is to punch a hole through thick hot iron. Another is to fold the metal around a space and forge weld the sides. A socketed tool may be formed by wrapping a flattened portion around a mandrel. Complex shapes become possible without casting. This is a profound advantage. Iron may refuse to melt conveniently, but forging gives smiths another path. You can stretch it, punch it, bend it, twist it, weld it, cut it, repair it. A damaged iron object can sometimes return to the forge and become something else. That matters when metal remains costly. A broken tool is not automatically rubbish. Heat it again, straighten it, weld it, cut away the damaged portion, turn it into a smaller object. Old iron can remain useful for generations. One scandalous aside is that archaeologists sometimes struggle to estimate how much iron a community originally possessed precisely because iron is so recyclable. Metal can be reforged repeatedly until the earlier object effectively disappears. A sword becomes a knife becomes a fitting becomes a nail. The archaeological record is left wondering where everyone put their iron. The answer may be that they kept using it. Your forge is now full of objects in different stages of life. Bars waiting to be shaped, broken tools waiting for repair, small offcuts saved carefully, scale and slag scattered on the floor, a worn hammer with a polished face, tongs shaped specifically for gripping different pieces. The toolkit expands because the material demands it. Specialized hammers appear, punches, chisels, drifts for enlarging holes, anvils with increasingly useful surfaces. Every new tool makes another type of ironwork easier. Iron begins helping to make more iron. That creates a powerful loop. A better hammer improves forging. A better chisel helps cut metal. Better tongs give more control. Improved tools allow more precise tools to be made. Technology starts building upon itself. The most valuable skill may simply be knowing when to stop. Hammer too long and you thin a section excessively. Reheat too many times and oxidation eats away more metal. Strike carelessly and you introduce cracks. The smith learns restraint. Not every blow should be heavy. Near the end, the hammer becomes lighter. Tap, turn, tap. Check the line. Another tap. The object moves from rough force toward refinement. You hold it at eye level. The glow is fading. Its shape is balanced. The edge follows a clean curve. The surface still shows the marks of making, but now those marks belong to a tool rather than a lump. You place it down. It cools gradually from red to black. For the first time, the iron has a clear purpose. Not ore, not bloom, not bar. a usable thing. That transformation depends less on spectacular discovery than on thousands of controlled hammer blow. Heat teaches the metal to move. Pressure teaches it to join. Practice teaches the smith when each is needed. The result rests quietly beside the hearth, darkening as it cools, while the hammer waits for the next stubborn piece of iron to explain itself. You follow the iron away from the workshop and onto the road. A finished tool can travel farther than the person who made it. A smith teaches an apprentice. A merchant carries a blade across a mountain pass. A soldier brings a damaged weapon home from a distant campaign. A migrant family settles beside a new river and rebuilds the kind of furnace they already know. Knowledge moves with all of them. This is how ironworking begins to spread across enormous distances. Not as a single announcement. Not as one secret handed from one king to another. It travels unevenly, carried through trade, imitation, migration, warfare, marriage, diplomacy, and the quiet movement of skilled people looking for somewhere better to live. You begin in Anatolia, where the landscape rises into mountains and plateaus threaded with old trade routes. Copper and bronze working already have deep histories here. Metalworkers know furnaces, ores, charcoal, casting, and forging. By the second millennium before the Common Era, iron objects appear in the region, although they remain relatively rare. Later traditions create a dramatic story around the Hittites. According to a once popular version of history, the Hittite kingdom possesses a closely guarded secret of iron working, almost like an ancient industrial patent. Then the Hittite political system collapses around the beginning of the 12th century before the Common Era. The secret escapes, and suddenly the Iron Age spreads across neighbouring lands. It is a wonderfully tidy story. History becomes suspicious whenever it becomes that tidy. Records confirm that iron objects and experimentation with iron occur in several regions before and during the period of Hittite power. There is little reason to imagine one kingdom holding a perfect monopoly over the entire technology. The Hittites certainly know iron. Their rulers value it. Texts connected with Anatolia refer to iron objects and iron being exchanged as prestigious material. But the spread of iron working appears more complicated than a locked royal secret suddenly leaking through a broken palace door. Scholars bicker over how important Anatolian specialists are in accelerating iron technology elsewhere, and how much development occurs independently among neighbouring metalworking communities already experimenting with similar furnaces. You walk southward toward the Levant. Here, coastlines, valleys, uplands, and caravan routes bring communities into constant contact. Ships move along the Mediterranean. Donkeys carry goods inland. Copper arrives from mining districts. Tin moves through complicated trade networks. Timber, pottery, oils, textiles, grain, and luxury objects change hands. A new metalworking technique does not need a formal embassy to travel through such a world. It only needs people. Suppose a smith from one town sees an iron knife made somewhere else. The object itself is a lesson. You inspect the shape. You test the edge. You examine the surface. Perhaps you ask where the metal comes from. Perhaps the owner lies. Trade secrets are not a modern invention, but even incomplete information can inspire experimentation. A foreign object proves that something is possible. That alone has power. Across parts of the Levant, iron becomes increasingly visible during the centuries following the disruptions near the end of the Bronze Age. Those disruptions matter. Major palace systems weaken or disappear. Long-distance trade networks change. Cities are destroyed, abandoned, rebuilt, or reorganized. Political authority fragments in some areas. Communities adapt. Bronze depends heavily on access to copper and especially tin. Tin can come from distant sources, and interruptions in trade make bronze production more difficult in places that depend on imported supplies. Iron ore, by contrast, is relatively widespread. That does not mean iron instantly becomes cheaper or easier. The labour involved is still considerable. But local access to raw material can become attractive when old supply systems are unreliable. You can picture the calculation. Tin must travel across hundreds or thousands of kilometres. Iron-bearing stone may exist in nearby hills. The nearby stone is infuriatingly difficult to smelt, of course. Nothing in metallurgy is allowed to be completely convenient. Still, once local smiths learn reliable methods, the advantage grows. A curious footnote appears in the earlier stages of this transition. Bronze does not simply vanish when iron becomes more common. Workshops can use both materials side by side, choosing according to purpose, cost, availability, and tradition. A household may contain bronze ornaments and iron tools. A warrior may carry equipment made from several metals. A craftsperson familiar with bronze can become part of the iron-working world without abandoning everything already known. The change is gradual. You move farther south toward Egypt. Here, metal has long been associated with wealth, administration, temples, and royal power. Gold is abundant by ancient standards. Copper and bronze are well established. Iron enters a society that already possesses sophisticated metalworking traditions. Yet ordinary iron production develops slowly. Egyptian craftspeople encounter iron objects before locally produced iron becomes widespread. Imported material, foreign specialists, diplomatic exchange, and contact with neighbouring regions all contribute to the process. The Nile helps goods move north and south. Mediterranean connections opened routes toward the Levant. Desert tracks connect mining zones and distant communities. An iron object can pass through many hands before reaching its final owner. Imagine a small blade arriving in a market. You pick it up. It looks darker than polished bronze. Perhaps the surface carries hammer marks. You compare its weight. You test it gently against wood. Someone tells you it was made far away. That makes it more interesting, not less. Foreign objects often carry prestige precisely because their origin is unfamiliar. One scandalous aside from ancient trade is that merchants have always been capable of improving a product's story when the story improves the price. A perfectly ordinary imported knife can become, after sufficient storytelling, the personal work of a legendary master from a mountain nobody present has ever visited. Human commerce remains comfortingly consistent, eastward. Mesopotamia offers another web of routes. Cities along the Tigris and Euphrates depend on exchange with regions beyond the river plains for many raw materials. Stone, timber, metal ores, and luxury goods arrive from elsewhere. Merchants and officials are accustomed to thinking across long distances. When iron becomes more useful, these networks help move both objects and knowledge. Assyrian expansion later intensifies the movement. Armies travel. Administrators relocate people. Tribute arrives from conquered territories. Craft specialists can be moved deliberately. An empire does not merely collect taxes, it collects skills. You can be a smith living in one town and suddenly discover that a king many days away has plans for your hands. Deportation and resettlement are harsh instruments of ancient imperial policy, but they also transfer technical knowledge. Potters move, builders move, metalworkers move, agricultural practices move, languages mix. Techniques that were once local become visible elsewhere. A council decree from an imperial centre may regulate workshops or demand equipment, but the deeper transfer still occurs person to person. Someone shows someone else how to prepare an ore, how to judge a furnace, how to weld an edge, how to recognize good metal. Those gestures travel farther than written orders. Now your route stretches southeast and east toward the Iranian plateau and the lands leading toward South Asia. Here, the story becomes even less suitable for a single line drawn on a map. Ironworking appears across a vast region with different local chronologies. Communities in the Indian subcontinent begin producing and using iron during the second millennium before the Common Era, with evidence varying by region and archaeological context. This matters because it challenges old assumptions that every major iron tradition must descend neatly from one Western centre. No agreement has been reached on whether some early South Asian ironworking develops largely through local experimentation, through transmission from Western regions, or through a combination of both. Arguments split along archaeological dating, technological similarities, or availability, and the reliability of particular excavated contexts. The landscape itself encourages experimentation. India contains extensive iron ore deposits, communities already skilled in ceramics, pyrotechnology, mining, and metalworking possess many of the practical foundations needed for iron smelting. Once the right furnace conditions are discovered and repeated, local traditions can become highly distinctive. You pass through a village where a furnace design looks different from one you saw hundreds of kilometers away. The shape changes, the clay changes, the bellows change, the ore changes, yet the goal is familiar. Create heat, control air, separate metal from stone. The fact that the solutions differ tells you something important. Technology spreads without remaining identical. A borrowed idea becomes local. A travelling smith adapts to different fuel. A community modifies a furnace to suit different clay. A new ore demands different preparation. Knowledge is translated into landscape. That is why archaeologists cannot simply find one furnace shape and trace it like footprints across the entire ancient world. Human beings modify what they learn. Beyond these regions, ironworking continues into Africa, Europe, Central Asia, and eventually much of the inhabited world. The timing varies enormously. Some communities adopt iron quickly. Others continue using stone, copper, or bronze effectively for long periods. There is no law requiring every society to embrace a new material at the first possible moment. New technology has costs. You need specialists, fuel, ore, tools, time, training. A community that already possesses excellent bronze working may see little reason to reorganize everything immediately. Another community with limited access to tin may find iron far more attractive. Local circumstances decide. Warfare also accelerates attention. An unfamiliar iron weapon captures interest, even when it is not automatically superior. You take it from a battlefield. A smith examines it. Perhaps it bends differently. Perhaps its edge has been hardened. Perhaps the socket or tang uses a construction technique worth copying. Weapons are technical documents that happen to be pointed, but farming tools may matter even more over the long term. An iron axe can clear woodland, a hoe can work soil, a sickle can harvest crops, a chisel can shape timber. When such tools become reliable and sufficiently available, ordinary people have reasons to seek them. The technology moves out of elite exchange and into daily work. Now the road carries iron in both directions. Finished objects travel outward. Broken objects travel towards smiths. Ore moves from mines. Charcoal moves from forests. Craftspeople move between settlements. Apprentices carry techniques into new households. A marriage can transfer knowledge as effectively as a caravan. A refugee can carry a craft farther than a merchant. A captured smith can unwillingly reshape an enemy's industry. A curious traveller can copy what nobody intended to teach. There is no single road. There are thousands. You hear different languages around the forge, but the sounds of the work remain strangely familiar. The hiss of hot scale, the thud of charcoal being poured, the bellows breathing, the hammer landing across mountains, river valleys, deserts, and coastlines. Communities learn to turn local stone into workable metal. The method changes slightly wherever it goes. The knowledge belongs to no single kingdom for long. Once enough people understand the principles, iron becomes difficult to contain. A technique can be guarded, A smith can be watched, a workshop can be controlled, but an idea that has crossed enough borders begins to live everywhere. You place an iron blade beside a bronze one. At first glance, the future does not seem obvious. The bronze blade gleams warmly in the firelight. Its surface is smooth. Its edges are clean. The metal has been cast into a precise shape by craftspeople who understand their material very well. The iron blade looks darker, rougher, perhaps slightly uneven. If someone tells you that iron is about to replace bronze, you might reasonably ask why. This is one of the great misunderstandings about the beginning of the Iron Age. Iron does not immediately appear as a miraculous superior metal. Early iron can be disappointing. It may bend. It may contain slag. Its quality varies. A well-made bronze tool can outperform a poorly made iron one. So the transition is not a simple contest in which iron marches into the workshop, defeats bronze, and claims the anvil before lunch. Bronze remains useful for a very long time. You can understand why by watching how it behaves. Bronze is usually an alloy of copper and tin, although ancient metalworkers also use other copper alloys. When heated enough, bronze becomes liquid. That gives the craftsperson an enormous advantage. You can prepare a mould, pour the molten metal, wait for it to cool, then remove an object already close to its intended shape. An axe head can be cast, a spear point can be cast, a decorative fitting can be cast with details that would take considerable effort to forge individually. Casting allows repetition. If your mould is reusable, several similar objects can be produced. Iron does not cooperate so neatly. You have to hammer it into shape. Every curve and taper requires work. Every socket or hole demands another operation. If the material contains hidden flaws, you may discover them only after spending hours on the object. Bronze, meanwhile, sits nearby behaving with the confidence of an established technology. Records confirm that bronze continues to be produced and used extensively in many societies long after ironworking becomes established. The name Iron Age can therefore be misleading if you imagine every bronze object suddenly disappearing. People use both. They choose according to need. A bronze vessel may remain preferable because bronze is easy to cast into thin, elegant forms. Bronze ornaments remain popular. Bronze fittings remain useful. Bronze can resist corrosion differently from iron and often develops a stable surface patina rather than simply rusting away in damp conditions. Iron has its own irritating habit, rust. You leave an iron object exposed to moisture and oxygen and the surface begins changing. Reddish-brown corrosion spreads. If neglected, the object weakens. Bronze corrodes too, of course, but the experience can be very different. To an ancient owner, this means iron requires care. Keep it dry, oil it if possible, store it properly, check the surface. A bronze object can sometimes survive conditions that make iron look personally betrayed by the weather. Oddly enough, this difference affects archaeology thousands of years later. Bronze objects often survive in recognizable condition, while ordinary iron can corrode until little remains beyond a rusty stain or mineralized lump. So a museum display can make bronze seem more common than it once was, simply because bronze has been more cooperative about remaining visible. The dead are not always equal witnesses. Neither are metals. You test the two blades. The bronze edge is hard. The iron edge may be softer than expected. Pure or nearly pure wrought iron is relatively soft. If you strike it against something hard, the edge can roll or deform. This seems rather inconvenient for the supposed metal of the future. The problem is carbon. Low-carbon iron can be tough and workable, but it does not automatically have the hardness you associate with good steel. Bronze, especially when properly alloyed and work-hardened, can make excellent cutting tools and weapons. This means early iron does not win because every iron sword is stronger than every bronze sword. That popular picture belongs more to myth than metallurgy. The real advantage becomes clearer when you stop looking only at the finished blade and look at the supply chain behind it. Bronze needs copper. It also usually needs tin. Copper is reasonably widespread, but high-quality tin deposits are much less common. That forces many societies to depend on long-distance trade. Imagine organising a bronze industry when your tin comes from a source hundreds or even thousands of kilometres away. The metal passes through merchants, ports, caravans, political boundaries, mountain routes, river systems. Every stage creates opportunities for interruption. A war closes a road, a kingdom collapses. Piracy affects shipping, a merchant network disappears, a distant mining region changes hands. Suddenly your bronze workshop has plenty of copper and very little tin. Iron ore presents a different possibility. Deposits are far more widespread in many regions. The ore can still be difficult to smelt, but once local craftspeople master the process, a community may obtain raw material much closer to home. You trade dependence on distant tin for dependence on local fuel, labour, and technical skill. That can be a very attractive bargain. A council decree proves that ancient states often take metal supplies seriously, regulating tribute, workshops, mines, and weapon production because reliable access to metal has political consequences. A ruler does not need to understand modern economics to recognize the problem. If your army depends on imported metal and the imports stop, your craftsmen cannot make reassuring speeches into spearheads. Local resources matter. Still, iron production is not automatically cheap. You need enormous amounts of charcoal, or must be mined and prepared. Furnaces must be built. Smelters must be trained. Smiths must spend many hours converting rough metal into tools. The advantage emerges gradually as the technology improves and production expands. You begin noticing iron objects in places where bronze once dominated. A simple knife, a small chisel, an axe, a spearhead, perhaps a nail. These ordinary objects tell you more about technological change than a royal sword does. Prestige objects can be made from rare materials precisely because they are rare. Everyday tools suggest that production has become broader. A farmer does not need a ceremonial marvel. A farmer needs something that works. You lift an iron hoe. It is not beautiful. That is almost the point. It can be repaired. It can be reforged. Its edge can be renewed. If the metal is available locally, replacing it becomes increasingly practical. The value of iron lies partly in abundance. A metal does not have to be perfect to transform society. It has to become available in useful quantities. A curious footnote appears when bronze recycling enters the picture. Bronze is extremely recyclable. A damaged bronze object can be melted down and cast again. This gives old metal lasting value. Broken weapons, worn tools, scrap fittings, and failed castings can return to the crucible. So even when fresh tin becomes difficult to obtain, existing bronze does not immediately disappear. Communities possess stores of metal accumulated over generations. A broken statue can become tools. Old tools can become new fittings. Metal remains metal. This helps bronze persist. You can almost imagine ancient households looking at a cracked bronze vessel and seeing not rubbish, but future inventory. Wastefulness is expensive. Recycling is ordinary. Iron can also be recycled, although usually through reheating and forging rather than easy remelting in early workshops. A broken iron object may become a smaller tool, a worn blade may become a knife. Useful fragments are saved. Both technologies develop economies of repair. The difference lies partly in raw material supply and production scale. As iron working becomes more reliable, smiths learn to improve the quality of their metal. They become better at choosing ores, better at managing furnaces, better at consolidating blooms, better at selecting different portions of metal for different jobs. An iron tool no longer has to be uniformly mediocre. The smith can combine toughness with harder working surfaces. That is when the comparison with bronze becomes more interesting. You examine an axe with an iron body and a harder cutting edge. The body does not need exceptional hardness. It needs toughness. The edge does. A skilled smith can concentrate the best material where it matters most. This is efficient. Expensive, high-quality metal does not have to fill the entire tool. You place it only at the working surface. The same principle appears in knives, chisels, and other edge tools. Iron working becomes not simply the production of iron, but the intelligent arrangement of different kinds of iron. Scholars bicker over how strongly shortages of tin and the disruption of Bronze Age trade networks drive the spread of iron, compared with improvements in iron technology itself. Some emphasize economic disruption. Others argue that iron working had already been developing and would likely have expanded even without dramatic political collapse. The two processes may reinforce each other. Trade instability makes local iron more attractive. Growing iron expertise makes communities less dependent on tin. History rarely chooses one convenient cause when several can work together. You can feel the change most clearly in an ordinary settlement. Bronze remains visible. A decorative pin catches sunlight. A vessel rests near a wall. A bronze fitting secures part of a piece of furniture, but the workshop contains more iron than it used to. Iron bars wait near the hearth. A farmer brings in a worn tool. Someone asks for a new knife. A carpenter wants a chisel repaired. The smith has a cue. That may be the real beginning of the Iron Age. Not a king raising a shining new sword. A craftsperson being asked to repair someone's hoe. One scandalous aside is that the heroic language surrounding ancient metals can make you forget how much technological history concerns extremely unromantic objects. Nails matter, hinges matter, clamps matter, hooks matter. The humble chisel may alter daily life more deeply than the ceremonial weapon displayed in a palace. A better woodworking tool helps make carts, doors, houses, furniture, boats, and agricultural equipment. An iron axe affects timber. An iron sickle affects harvest. An iron plough component affects soil. The consequences spread quietly. Bronze does not lose its usefulness. Its role changes. In some places it becomes increasingly associated with vessels, ornaments, sculpture, fittings, and specialized objects, while iron becomes common in tools and weapons. Elsewhere, the balance differs. Local resources decide, tradition decides, price decides, craft knowledge decides. There is no universal morning when everyone wakes up and agrees to stop using bronze. Instead, generations live inside the overlap. A grandfather trusts bronze, a daughter uses both. A grandson works in a forge where iron is ordinary. Nobody needs to announce a historical age. They simply choose the material that suits the task. You run your finger carefully along the blunt back of the iron blade. It is darker than bronze, less elegant, perhaps, but its future lies in numbers. More ore can be found. More furnaces can be built. More smiths can learn. More households can eventually afford tools that once represented considerable wealth. Iron wins slowly, not because bronze suddenly fails, not because every early iron object is superior. It wins because persistence, local resources, repairability, and improving skill gradually turn a difficult metal into an increasingly practical one. The two blades still lie beside each other. Neither has vanished. One represents an old craft at the height of its refinement. The other represents a difficult material whose possibilities are only beginning to widen. You hold two iron knives that look almost identical. Both are dark. Both have been hammered into shape. Both carry the faint scars of the forge. Yet when you test their edges, one bends and dulls quickly while the other bites cleanly into wood and keeps its shape. Something has changed inside the metal. You cannot see it. You cannot smell it. You cannot point to a bright ingredient mixed into the surface. But the difference is real. The harder blade contains more carbon. This is where ironworking becomes considerably more mysterious. Ancient smiths do not need to understand carbon atoms to discover that iron can change its character when it spends enough time surrounded by hot charcoal. A piece that begins soft can become harder. A cutting edge that once folds can suddenly hold. The transformation seems to happen inside the forge itself. You push an iron blade deep into glowing charcoal. The bellows breathe, sparks drift upward, the blade turns red, then orange. At high temperatures, carbon from the charcoal-rich environment can slowly enter the outer layers of the iron. Modern metallurgists call this carburization. To you, standing beside an ancient hearth, it is simply one of those strange things the fire sometimes does. The effect is not instant. Carbon moves into solid iron gradually. The hotter the metal and the longer it remains in the right conditions, the deeper the carbon can penetrate. So perhaps the first discovery happens accidentally. A blade is left in the charcoal longer than usual. Maybe the smith is distracted. Maybe another tool needs attention. Maybe the customer has arrived early and is enthusiastically explaining how simple blacksmithing appears from the doorway. The blade remains buried in the hottest part of the fire. When it is finally finished and tested, the edge behaves differently. It is harder. Now the real challenge begins. Can you make that happen again? Records confirm that ancient ironworkers eventually learned to produce steel, meaning iron containing enough carbon to behave differently from relatively pure wrought iron. The word steel describes a range of materials rather than one single recipe. A small change in carbon content change hardness, strength, flexibility, and response to heat treatment. This creates enormous possibilities. It also creates enormous confusion. You can forge two pieces from the same bloom and end with different properties. One portion may have absorbed more carbon during smelting. Another may have remained nearly pure iron. Reheating them in charcoal can alter them further. Then cooling speed changes their behavior yet again. The metal begins to feel almost alive. It remembers how it was heated. It remembers how it cooled. You learn this not from theory but from consequences. A blade comes out excellent. Another cracks. Another remains soft. Another becomes hard at the edge but tough along the spine. That last combination is especially useful. A cutting tool needs hardness at the working surface, but excessive hardness throughout the entire object can make it brittle. You want the edge to resist deformation. You want the body to survive shock. The best object may therefore contain more than one set of properties. A skilled smith starts exploiting this deliberately. You take a softer iron body, add a harder carbon-rich edge, heat the pieces, forge weld them together. Hammer until the seam disappears. Now expensive high-quality material is concentrated exactly where it matters. The blade does not need to be made entirely from harder steel. Only the cutting portion needs exceptional hardness. This is economical and clever. A curious footnote is that ancient smiths can create extremely sophisticated composite objects, while lacking any modern language for carbon percentages, crystal structures, or phase transformations. You do not need to name a process to control it. A baker does not need molecular chemistry to know when dough has risen. A potter does not need an equation to judge a kiln by flame color. And a smith does not need a microscope to know that this particular bar behaves beautifully under the hammer. The forge becomes a place of memory. This ore, that charcoal, this heating color, that cooling method, a combination that works is repeated. A combination that fails becomes a story told to apprentices, sometimes with more dramatic language than strictly necessary. You can hear the warning row, do not leave the edge too long. Do not cool that bar too quickly. Do not use that piece for a chisel. Practical categories grow around repeated experience. Then comes quenching. You heat a carbon-rich piece of iron until it glows. Instead of allowing it to cool slowly in the air, you plunge it into water. The sound is immediate, a violent hiss. Steam bursts around your hands. The glowing colour vanishes. The metal cools with shocking speed. If the carbon content and temperature are right, the iron can become dramatically harder. This happens because rapid cooling traps the internal structure of the steel in a hard form. You do not know that. What you know is that the blade now resists scratching differently. Its edge lasts longer. Strike it carelessly, however, and another problem appears: it may crack. Hardness has a price. Too hard can mean too brittle. One scandalous aside from early metalworking is that the most impressive-looking heat treatment can also be the fastest way to ruin hours of labour. Imagine spending a day shaping a blade. You heat it carefully. You plunge it into water. There is a hiss. A small crack appears. The entire workshop becomes very quiet. The blade has learned hardness. Unfortunately, it has also learned how to become two blades. Smiths begin experimenting with cooling methods. Water is fast. Oil can cool more slowly. Different liquids behave differently. Even water temperature can matter. So can the thickness of the object. A thin edge cools faster than a thick spine. The same quench can produce different results across one blade. Ancient craftspeople may not explain any of this scientifically, but repeated experience reveals patterns. Then someone discovers another subtle trick. A hardened blade can be reheated gently after quenching, not to forging temperature, only enough to reduce some brittleness while preserving useful hardness. This process is tempering. It is one of metallurgy's elegant compromises. You deliberately soften something slightly to make it better. The beginner might find that absurd. Why harden it and then soften it? Because the hardest possible blade is not necessarily the best blade. You want balance. Hard enough to hold an edge, tough enough not to crack. The difference between those goals becomes part of the smith's judgment. Steel therefore emerges not from a single discovery, but from a collection of linked observations. Charcoal can change iron. Long heating can increase hardness. Rapid cooling can increase it further. Rapid cooling can also create brittleness. Gentle reheating can restore toughness. Different regions of the same object can be treated differently. Once these relationships become understood through practice, the smith gains extraordinary control. You watch a blade move through the sequence. First, it is forged, the edge is shaped, the spine is corrected, then it returns to the fire. The smith watches the colour carefully. There is no thermometer. The glow is the guide, a little darker, a little brighter. Now, the blade comes free. For an instant it hangs in the air, orange against the darker workshop. Then it enters the quenching liquid. Hiss. Steam rolls upward. The smell changes. If oil is used, there may be smoke and a sharp, burnt scent. The blade emerges black and wet. You cannot see the internal transformation. The surface gives no grand announcement. The test comes later. The edge is polished. A file is drawn across it. The smith listens. A softer piece allows the file to bite. A hardened surface resists. Sound becomes evidence. Touch becomes evidence. The metal itself answers the question. Historians still argue whether some early steel production is primarily accidental carburization during smelting and forging, or whether specialist smiths in certain regions developed deliberate methods much earlier than traditional chronologies once suggested. The archaeological difficulty is considerable. Steel rusts. Heat treatment can be altered by later fires. Tiny samples may not represent an entire object. A blade can contain several different microstructures from edge to spine. Even a single knife may preserve a complicated manufacturing history. So scholars examine surviving metal under microscopes, searching for clues left by heating, carbon content, welding, and cooling. The ancient smith has no microscope. The ancient smith has an edge test. If the knife cuts better, the technique matters. That practical standard encourages innovation. There is another route to better steel. Instead of merely adding carbon to the surface of finished iron, some traditions eventually produce steel with carbon distributed more deeply throughout the material. In parts of South Asia, highly sophisticated crucible steel traditions develop, in which iron and carbon-rich materials are heated together inside sealed containers. The temperatures and conditions allow a more controlled high-carbon steel to form. This is a major technical achievement. The resulting material can later be forged into blades renowned far beyond the regions where the steel itself is produced. Trade carries these high-quality steels across long distances. A merchant may know little about the furnace chemistry. He knows the ingot commands a good price. A smith receiving it knows immediately that it behaves differently from ordinary iron. It may require careful forging temperatures. Treat it badly, and you waste expensive material. Treat it well, and the result can be exceptional. Steel creates new hierarchies of craft. The best smith is no longer merely the person who can shape iron. It is the person who can read subtle differences within iron. That knowledge can be guarded carefully. A workshop develops habits outsiders cannot easily copy. The exact position in the hearth, the length of the heating, the colour before quenching and the sound of the hammer, the angle of the edge. A stranger watching may see all the movements and still fail to reproduce the result. Skill hides inside timing. A council decree proves that states eventually value skilled metalworkers enough to supervise, employ, relocate, or support them, particularly where weapons and tools become strategically important. Yet rulers cannot command excellent steel into existence by simply demanding it. The knowledge remains stubbornly practical. A master has to teach it. An apprentice has to fail repeatedly. Hands have to learn. The spread of better steel also changes what iron tools can accomplish. A harder chisel cuts wood more effectively. A durable knife stays sharp longer. An axe edge survives repeated impact. A sickle can be thinner and more efficient. A weapon can combine a resilient core with a hardened edge. The improvement is not only military, it enters workshops, farms, kitchens, forests, and construction. Better edges change labour. You need fewer pauses for sharpening. A tool lasts longer. Hard timber becomes easier to shape. Repeated work becomes less frustrating. That may sound modest compared with famous swords, but civilization spends far more time cutting wood, harvesting grain, and repairing things than participating in dramatic duels. The ordinary edge matters. You turn the finished blade in your hand. It does not look magical. The surface is dark. The shape is practical. Nothing reveals the invisible carbon locked inside. Yet this small addition has changed iron completely. The charcoal that once served only as fuel has become an ingredient. The cooling water that once ended the heat has become part of the manufacturing process. Even the speed of cooling has become a tool. Fire is no longer simply making iron soft enough to hammer. It is changing what iron is. You test the edge once more. It holds. The metal has acquired a memory of flame, charcoal, water, and careful timing. And inside that quiet, hardened edge lies one of the most important discoveries ancient craftspeople ever make. Iron can be taught new behaviour. You wake to the sound of iron meeting wood. Not on a battlefield, not in a royal workshop, just outside an ordinary house where someone is repairing a cart. The hammer strikes an iron fitting. A wheel turns, a hinge squeaks. A knife rests beside a loaf of bread. These are the quieter signs that iron has changed human life. The greatest transformation does not happen when a king receives a magnificent sword. It happens when metal becomes ordinary enough to enter the hands of farmers, carpenters, builders, cooks, herders, miners, and craftspeople whose names will never appear in any chronicle. Iron settles into daily routines. You walk toward a field. Morning moisture still clings to the grass. The soil is dark beneath your sandals, and somewhere nearby you hear the repetitive scrape of a tool cutting earth. A farmer works with an iron-edged hoe. The tool does not look revolutionary. It looks tired. The handle is polished from years of hands gripping the same wood. The iron edge has been sharpened repeatedly. Small dents remain along the surface. Yet that edge matters. Iron tools can be repaired and reforged, and as production expands, they can become available in quantities that transform agricultural work. Records confirm that iron farming implements become widespread across many ancient societies. Though the pace differs greatly from region to region, you see axes used to clear trees and branches, hoes break compacted ground, sickles cut grain, iron-tipped digging tools open stubborn soil. In some places, iron components improve ploughs designed for difficult terrain. None of these tools creates agriculture. Farming is already ancient. What iron can do is change the amount and kind of labour required. A durable edge survives tasks that quickly exhaust softer materials. A farmer can sharpen the tool again rather than replacing the entire object. A local smith can repair damage. The relationship between field and forge grows closer. You finish harvesting and carry a damaged sickle into the settlement. The smith does not need to make a new one. The edge can be straightened. A worn section can be repaired. A new harder strip may sometimes be welded into place. The tool returns to the field. This cycle of use and repair gives iron a long life. A curious footnote is that one object may pass through so many repairs that very little of the original tool remains. The handle changes. The edge changes. A cracked portion is cut away. Another piece is welded on. Eventually, asking whether it is still the same tool becomes less a question for the blacksmith and more a way to ruin a perfectly pleasant evening with philosophy. You continue toward the carpenter's workspace. Here, iron is changing wood. A chisel bites into a beam, an auger opens a hole, a small axe trims a joint. Iron nails and clamps hold structures together. Better woodworking tools influence houses, carts, boats, furniture, storage chests, gates, agricultural equipment, and dozens of objects that rarely receive dramatic historical attention. The effect multiplies. An improved metal tool makes a better wooden tool. A better wooden frame supports a better roof. A stronger cart carries heavier loads. A better wheel allows goods to move more reliably. Iron does not act alone. It strengthens an entire network of crafts. You hear a saw somewhere farther down the lane. A door swings on fittings. A bucket hangs from an iron hook. A chain secures an animal. The metal has become part of the architecture of ordinary movement. Markets feel the change too. More iron means more specialized work. Ore has to be mined. Charcoal has to be produced. Furnaces need builders. Smelters require assistants. Smiths need apprentices. Finished objects have to be exchanged. A metal industry creates jobs long before anyone invents the phrase employment sector, which is probably fortunate for everyone's peace of mind. You enter a marketplace. The smells arrive first. Bread, smoke, animals, herbs, leather, hot metal from a nearby forge. On a cloth lies a collection of small iron objects, knives, awls, needles, buckles, hooks, simple fittings, perhaps a pair of shears. Each object solves a modest problem. Together, they alter domestic life. An iron needle helps sew thick material. An awl pierces leather. A knife prepares food. A hook supports a cooking vessel. A lock protects a storage room. Iron becomes useful precisely because it can disappear into routine. You stop marvelling at the material. You simply expect the door to have a latch. That is technological success in its most complete form. The wonder vanishes into habit. One scandalous aside is that historians have traditionally spent far more ink describing iron weapons than iron nails. The sword is exciting. The nail rarely appears in heroic poetry. Yet remove nails, clamps, hinges, chisels, and agricultural tools from an ancient society, and daily life becomes inconvenient with impressive speed. An iron nail has no dramatic biography. It quietly holds something together. Human civilization requires a great deal of quiet holding together. Mining also expands. Once communities demand more iron, they need more ore. Shallow deposits may be worked first. Open pits deepen. Tunnels may follow veins into hillsides. Miners learn which deposits are worth the labour, or moves along paths towards smelting sites. Fuel moves too. This can reshape landscapes. Charcoal production consumes woodland. Intensive smelting can place serious pressure on nearby forests, especially where large industries operate for long periods. The furnace does not only transform ore, it transforms environments. Trees become charcoal. Charcoal becomes heat. Heat becomes iron. Iron becomes axes that can cut more trees. You can see the uncomfortable circle. Ancient communities respond in different ways. Some production shifts as local wood becomes scarce. Some states manage forests. Some workshops rely on wider supply zones. No agreement has been reached on how severe iron production alone was as a cause of deforestation in many specific ancient regions, because farming, shipbuilding, construction, grazing, and ordinary fuel use also remove woodland. The impact depends on population, scale, climate, and local ecology. Still, a busy iron industry leaves more than slag behind. It leaves altered hillsides. Iron also enters warfare more deeply. As production increases, larger numbers of spearheads, arrowheads, swords, armour components, and fittings can be manufactured, but numbers matter as much as quality. A society able to equip many soldiers with adequate iron weapons may gain advantages over one relying on smaller supplies of expensive metal. The effect is not automatic. An iron sword does not guarantee victory. Training matters, organisation matters, food matters, leadership matters, terrain matters. A frightened person holding excellent steel remains a frightened person holding excellent steel. Still, reliable access to metal affects what armies can sustain. Iron tools support armies even when they are not weapons. Axes clear roads, picks prepare defences, nails repair carts, knives prepare food, fittings strengthen wagons. The military importance of iron reaches far beyond the blade. States notice. Rulers seek control of mines. Taxes can be collected in metal or finished goods. Workshops may produce equipment for palaces, temples, or armies. Skilled smiths gain political importance because their knowledge cannot be replaced as easily as raw material. You can seize a pile of ore, it will not smelt itself. A council decree proves that governments in several ancient regions eventually regulate craftsmen and strategic resources, revealing how deeply metal production becomes connected with administration. But iron does something else that kings cannot fully control. It spreads practical power downward. A village with capable smiths can make and repair its own tools. A farmer with a durable axe can reshape land. A carpenter with strong chisels can undertake ambitious work. A household with accessible knives, needles, hooks, and fittings possesses capabilities once restricted by scarcity. This does not make society equal. Far from it. Wealth, rank, slavery, taxation, land ownership, and political authority remain powerful forces. Iron is not a social miracle, but abundant tools change what ordinary labour can accomplish. Your day follows those tools, so you cut food with iron, you open a gate held by iron fittings, you work soil with an iron edge, you repair leather with an iron awl, you split wood using an iron axe, you secure an animal with an iron chain. At night, perhaps an iron latch closes your door. The metal surrounds you without requiring attention, and that is remarkable when you consider what has been achieved. A dark mineral in the hillside is mined. It is crushed, prepared. Combined with charcoal, reduced inside a furnace, pulled out as an imperfect mass, compacted, forged, sorted, perhaps hardened, then shaped into something as modest as a hinge. So much knowledge hides inside the movement of one door. Scholars still argue whether the spread of iron should be understood mainly as a technological revolution, an economic transformation, or a gradual adaptation unfolding differently in each region. The word revolution can mislead. In some places, adoption is rapid. In others, centuries pass while old and new materials coexist. Some communities produce iron locally. Others import it. Some become famous for exceptional metallurgy. Others use simple tools made from modest metal. There is no single Iron Age experience. There are many. You see this most clearly when you leave the palace behind. History often preserves the king's name. Daily life preserves the smith's work. The ruler may be forgotten by everyone except specialists. The basic forms of the smith's tools continue for centuries. Hammer, tongs, anvil, chisel, fire. The essential gestures remain recognizable across enormous distances of time. You could stand in an ancient forge and understand much of what the smith is doing without sharing language. Heat, grip, strike, turn, listen. The craft becomes part of human inheritance. Iron also changes trade. Ore moves outward from mining regions. Finished tools move inward. Specialized steel can travel enormous distances. Merchants learn which workshops have good reputations. A superior blade may become associated with a particular town or region. Craft prestige becomes economic value. Counterfeits probably follow, because wherever humans discover quality, another human eventually discovers the label. Markets connect distant expertise. A tool made from ore mined in one region may be forged elsewhere, sold in another town, carried by a traveller, repaired by a different smith, and finally recycled into another object. Iron circulates. Its story becomes impossible to assign to one person, and perhaps that is the most fitting conclusion. There is no lone discoverer standing at the beginning of iron. There are observers, miners, potters, charcoal makers, smelters, smiths, merchants, farmers, apprentices, travellers. Thousands of hands contribute small pieces of knowledge. One person notices a strange mineral, another controls hotter fire, another discovers better airflow, another learns how to remove slag, another recognizes useful hardness, another teaches a child. The discovery is collective, slow, untidy, human. You look around the settlement as evening arrives. Smoke rises from cooking fires. A smith finishes one final repair. Someone closes a wooden gate. An iron latch drops into place with a quiet click. That sound is small, almost nothing, yet inside it rest generations of experiment, failure, memory, and skill. The metal has stopped being mysterious. It has become useful, and usefulness, repeated millions of times, is how iron quietly remakes the human world. The forge grows quiet now, and the final glow settles beneath a soft covering of ash. You no longer need to follow the hammer or wonder which stone will change inside the fire. The work is finished for tonight. Around you, fields darken beneath a calm sky. Doors close gently, and the last tools are set down where patient hands can find them again in the morning. You can let the distant ringing fade until it becomes no more than a memory, then let even that disappear. The iron cools, the charcoal dims. Footsteps soften on the earth. Nothing asks anything more from you. The long road of discovery has come to rest in ordinary objects, quiet rooms, and familiar human hands. Allow your thoughts to settle there, warm and unhurried, while the night stretches peacefully beyond the sleeping village, and the final spark in the forge slips gently into darkness.